Okay, so as I mentioned, today's lecture is going to be about classification, and in this case using mixtures of Gaussians. So we've seen already one model, k-nearest neighbor for classification, simplest model possible. Now we're seeing a statistical model which is based on mixtures of Gaussians, and in fact this model is in the family of what are known as generative models. Okay, so with respect to generative models, we've already seen for regression a statistical linear regression model, and now we're going to do something similar for classification. But just to illustrate what I mean by generative models and how they can be used for regression and classification, let's draw a picture that will illustrate those models. Okay, so with regression, we talked about linear regression, and here we saw it both from the perspective of optimization, where we just want to minimize the distance with respect to a line. So I guess, yeah, for regression, the idea is that you've got data, right? You're fitting a curve, and if it's linear regression, you're fitting a line that hopefully goes through every data point, or otherwise comes as close as possible. And from an optimization perspective, you just want to minimize the distance. But we also saw the statistical perspective, where there we said, well, for regression, the story could be that we suspect that the underlying function is linear. So let's say that this is our true underlying function. It's parameterized by W transpose X. And now, whenever we have a data point, so here, let's say that the inputs are the x-axis, the output are the y-axis, and let's say I've got a data point x. Now, if my function is correct, I would expect the data point to be precisely on the line. But the reality is that the data that I observe is measured through some sensors, and sensors are never perfect. Right? So there's often some inaccuracy, some noise that creeps in. And then we said, well, what if we model this with a Gaussian distribution? Right? So the noise in the measurement perhaps could have a Gaussian distribution. So what this would mean is that if I have a data point x, even if I know what is a true underlying function, what I would likely observe is that the output is sampled from a Gaussian distribution that might have a shape like this. So here, what I just drew, think of it as a little Gaussian with respect to this vertical line that indicates that most likely I would get a measurement that is at the line, but then, could also be a little bit away. And then if it gets too far from the line, then it's very unlikely. Right? So for different data points, then I would get like this, some Gaussian distribution. And it would be the same like this at every data point. So now, if I wanted to generate some data, so let's say I've got some input x, and then I'm just wondering what I might observe. So then I would sample from this Gaussian, and perhaps I might get a point that is here. So it's not exactly on the line, but it's in the region that is quite likely. And same thing for this one here, and then perhaps this one here, and so on. So here we can say that this is a generative model because I could use my model, in fact, to simulate the creation of a data set. And now you might say, well, what's the point of doing that? Don't we start with a data set? But it turns out that there's lots of applications like text generation, image generation, where it's actually interesting and very useful to be able to generate data. Like let's say you've got a conversational agent, and then you would like to generate a response that is similar to responses that you might find into a data set of message response pairs, right? So then this would be an example where you would like to generate some data, and having a generative model for this can be quite useful. The same thing could be done with images. So there's been a lot of interest in recent years where, let's say, we have images of people, and then we would like to generate similar images of people that perhaps don't exist. These would be, made-up people, right? Made-up faces. Can we get a model to generate pictures of people in this fashion? And then, so this is where generative models become quite interesting, because then they can generate, for certain tasks, data that is similar to the data that you would have in the training set. Now, in this case here, you might say, well, I guess this is never going to generate text or images, right? But the principle is the same, right? So it would be possible to use this model to generate data similar to the training set. Okay, so that's what we did with linear regression. And now let's consider classification. So for classification, I could start by saying, let's say that in some domain, I've got 3 possible classes. I'm going to denote them by A, B, and C. Okay, so let's say that I've got 3 classes. And now, in this case, let me use the first axis to denote the first component of my input, x1, and then the second axis to denote the second component of my input. Okay, so this is a little bit different than this plot. So this plot here had input, output. Here, this is both input, input. Okay, and now I'm going to draw. Okay, the assumption is that if I'm doing classification, perhaps every data point is going to be associated with one class, but then when I measure the inputs, it might not be accurate. And then normally I would expect every data point in class C perhaps to be centered right here, but then maybe there's a Gaussian distribution that could correspond to noise in the measurements of my inputs, and then as a result, I might have data that follows a Gaussian distribution centered right there. Okay, so this would be for C. I could have something similar for A, and also something similar for B. Okay, so these here would correspond to contour lines of surfaces that would come out of the board that would correspond to distributions for where the data associated with class A is located. Same thing for C, and same thing for B. Okay, any questions regarding those drawings? Very good. Okay, so based on this idea that our data could be in different regions where for each class there's a distribution, now we could construct a probabilistic model where we could say, well, a priori, when I haven't looked at a single data point and then I'm just guessing, what might be the class of a data point, I could have a prior distribution. I'm going to denote this by the probability of C, so the probability of the class before I look at a data point. And then once I have a data point, I could say, well, what's the probability that if I'm picking a point from a class C, that it would be located at certain locations, then I could have a class conditional distribution that could be used to generate points from that class. And if we have like this a prior and a likelihood, then I can compute a posterior distribution to essentially estimate what might be the probability of the class for a given data point. So here I can compute the posterior using Bayes' theorem, where I multiply the prior by the likelihood. I renormalize. So here the denominator is really just a normalization constant, and I can get like this an estimate or a prediction for the class of this data point. Now on this slide, we have to be careful because what I'm talking about here is not Bayesian learning. So I am using Bayes' theorem, but here this is more using Bayes' theorem for inference, where I'm trying to simply estimate what is the probability of the class for a given data point. Whereas when we talked about Bayesian learning, this was more in the context of having some parameters of a model, and then I want to estimate the parameters of this model using Bayes' theorem. So here, we haven't discussed the parameters of this model yet. We're going to do this in a moment. But then, really, all we're doing here is inference to compute the posterior probability of a class. Okay, so this is Bayesian inference as opposed to Bayesian learning, in the sense that we're not learning parameters, we're simply estimating the class of a data point. Okay, any questions regarding this? Okay, very good. All right, so in this model, we're going to make some assumptions. First, let's assume that the number of classes is finite, and in fact that they're categorical. So then what's a natural type of prior that we could use is a multinomial distribution. Right? So multinomial distribution is just a distribution over a finite number of possible outcomes that are categorical. So a good example would be, let's say that you have a coin, you can flip it and get head or tail, right? So this would be, you could have a Bernoulli distribution, but now if you generalize this to multiple outcomes, like with a dice where there are 6 faces, right, then there would be a probability for each face, and then we could use a multinomial distribution for this. So here I'm going to use pi k to denote the probability of class k. Okay, and that's just a number between 0 and 1. Now let's also assume that we have data that is from some space. Could be anywhere in the reals, and let's say that this data has d dimensions. So now we'd like to have a class conditional distribution that would tell us for a given class where the data is likely to be in that space. And then we're going to start here by assuming that this class conditional distribution is a Gaussian distribution. Okay, so I've got my class. Given a class, what's the probability of the data being in some region or being in some location? Perhaps we can model this with a Gaussian. And that's essentially what I drew on the board here. Okay, so these Gaussian distributions are examples of class conditional distributions that are modeled by Gaussians. Okay, I'm also going to make the assumption that each Gaussian distribution has the same covariance matrix, capital sigma. Okay, so with this assumption, then I can write the class conditional distribution as being proportional to an exponential of this form. Okay, so here the assumption that we have the same covariance matrix for every class is going to become important to simplify some terms later on, so we're going to come back to this. But more generally, obviously, we could consider different covariance matrices for different classes. It's just that for now, we're starting simple, so I'm going to make this assumption. We're going to see how it helps us, but generally speaking, we might not want to make that assumption. Okay. All right, so any questions regarding those assumptions? Everything is good? Okay, let's continue. All right, so now that we have defined the prior, and we've also defined the likelihood, so the prior is a multinomial, the likelihood is a Gaussian distribution, then we can compute the posterior to do inference. And here again, it's not about Bayesian learning. This is more about doing inference to estimate the probability of each class given a data point. Right? So then the posterior would just be the product of our prior by the likelihood where we renormalize. Now this expression, I can simplify it a little bit. So if I rewrite this term by expanding it in this way, and then I do the same thing for the denominator, it turns out that I can simplify the first term. Right? So here, this is pi k times an exponential. In that exponential, there's 3 terms. The first term does not depend on the class. so I could in fact pull it out in front. And then same thing in the denominator. The first term does not depend on the class k, so I can pull it out in front of the summation, and then this will cancel. Right, so I can cancel the first term, and then I'm left with the other two terms. Now these other two terms, if I decide as well to restrict myself to just two classes, we're going to come back to multiple classes in a moment, but for now, if we restrict ourselves to just two classes, I'm going to denote them here by ck and cj, then I can rewrite this expression by dividing both the numerator and the denominator by the numerator, and then I'll get this expression. Okay, so now you might be wondering, where the hell am I going with this? I mean, this expression is not particularly good looking, but if you just hang on for a moment, this expression, if I reorganize it a little bit, and then I notice that this exponent is really linear in x, then I can rewrite this expression as just w transpose x plus w naught, where I'm going to define w to be this expression. So that's the coefficient of x in here. And then w naught is just going to be the constant part that does not depend on x in here. Okay. So I did all of this to get my posterior into a nice form here, 1 divided by 1 plus e to the minus w transpose x plus w naught. Now, does anybody recognize what is this function? So this is a function that is actually very used very often in neural networks and other types of models. Does anybody know what is the name of this function? Yes? You're close. That's not exactly the one I was looking for, but that could be another function we could arrive at with different assumptions. So yeah, so it's not the logit. What is it? Yeah, it's the sigmoid function. Okay, so I guess it's the logistic sigmoid function. And this function is actually quite popular in neural networks. And now we just saw a derivation where we arrive precisely at the logistic function. So the logistic function is typically denoted by the sigmoid of some argument, and then it turns that into 1 divided by 1 plus e to the minus of that argument. Now in our case here, this argument is going to be linear in x. This is what I had on this slide, right? So here we've got a linear expression in x, but then more generally, the logistic sigmoid gives us this expression. Okay, and this function is interesting. We're going to draw it, and then you'll understand why, after that, in neural networks, people often use this function, even though it might not be related to mixtures of Gaussians. Okay, so the logistic function, so let's put a on the x-axis. We're going to have sigmoid of a on the y-axis. So it's a function that starts near 0, then it goes up, crosses, and then asymptotically reaches 1. Okay, so here it reaches roughly 1. And then it crosses the y-axis at 0.5. Okay, so this function has a property that essentially takes any real number, right? So the input here, which is a, denotes any real number, and then it will produce an output which is squashed between 0 and 1. So it starts near 0, and then it reaches 1 asymptotically. So it's going to be between 0 and 1. And that's part of the reason why this function is very popular in the context of neural networks, because often you want to compute an output that you want to interpret as a probability. So it better be a number between 0 and 1. And then the logistic function, logistic sigmoid, does that. Okay. Now, this function has a particular definition that we just saw on the slides. Right? So this is its definition, but where does it come from? Right? So very often in neural networks, people create these layers, and then there might be a logistic layer at the end to produce some output that can be interpreted as a probability distribution. But where does it come from? Why do we use this particular form? Because another form that was mentioned just earlier would be the logit function. So there's all kinds of functions that you could actually use to squash the output between 0 and 1. But here we can see that in the case of the logistic function, it comes from essentially computing this posterior distribution in the context of mixtures of Gaussians. So that's the origin. That's where it comes from. And then its particular definition, right, can be obtained in this way. And here I'm treating essentially the coefficients of x as parameters, w. We're going to see later on y. And then the constant part, I'm treating this as w naught. And then in the context of mixtures of Gaussians, right, then we can see how the mean and the covariance matrix, as well as the class probabilities, can be combined together to give us those parameters w and w naught. Okay, any questions regarding the logistic sigmoid? Okay, very good. All right, let's look at two more pictures here. So again, if we're doing classification and then we have data and we're trying to find for each data point which class it belongs to, what is natural is to have a class conditional that is Gaussian. So here, this is one class that's red, and this could be its Gaussian distribution for where the data of that class happens to be. And then we might have another class that's denoted in blue here. And naturally, you see if we have two classes, red and blue, this is their Gaussian, a nice bell shape. Now, if we want to compute a posterior, right, so if we're given a data point that happens to be more on the left side, then it's natural that the posterior would have a higher probability for the red class. So here this is in red, the bottom part is in blue. So that indicates that we have a high probability for the red class, and here that we have a high probability for the blue class. And then overall, the posterior here would be the probability for the red class, right? So that's how it goes from 1 down to 0, depending on, how we go from the left to the right. Okay, so these class conditionals, again, these are Gaussian distributions. This is a picture in 3D, so you can see the nice bell shape. But this is essentially the same as what I had on the board before, where here I just drew it in 2D, right? So there I've got contour lines, but this is the same thing in 3D that gives you the nice bell shape. And then if we're in 3D, instead of having just a function that goes up from 0 to 1, then here we would have, I guess, yeah, this is a curve that goes up from 0 to 1. So here I'll have instead a surface. In this case, it goes from 1 down to 0, but it all depends whether we're looking at a property of the red class versus the blue class. But it's a nice surface that is kind of like a smooth cliff, right, that starts high and then dips and then goes along 0, right? And that's the generalization in higher dimensions compared to what I drew on the board. Yeah?
Are the lower axes common at the bottom?
Say that again. So the axes at the bottom, are they
Are they common between the two?
Yes. So here, this axis is the same as this one, and this axis is the same as this one. Yeah, so we have the same axes at the bottom, and yeah, the y-axis has a different interpretation, right? So here this is simply the probability of the red class, so that's why this axis goes from 0 to 1. Here this is the probability density for each class. So we've got a probability density for the red class, the one for the blue class, and then that doesn't have to go from 0 to 1, right? Yeah?
So on the, as we go like left and towards the board for the posterior, does it tend towards 1 because we're much farther from blue than we are from red?
Exactly, yeah.
Although red also diminishes in its own Gaussian, we're still much farther from blue than we are from red. So
Yeah, okay, very, very good point. Because yeah, here it's clear that when we're near the peak of the red class, then it makes sense that the red class should dominate. But once we pass the peak, and now the red class is also going down, yeah, why are we thinking that points in this region, right, would be more with the red class than the blue class? Because the red class is also going down. But the point is that both classes are going down, and then the blue class has already been going down much more than the red class. So here it would depend on what is the variance of those two Gaussians, but I am making the assumption that we've got the same variance or the same covariance matrix for both of them in this plot here. So if they have the same covariance matrix, so then here we're still closer to the red class than the blue class. So we're still going to have a higher likelihood for the red class compared to the blue class. And that's why this remains high and close to 1. Yeah. OK. Any other questions? Yes?
Where do we get the definitions of the red and blue class and their coordinates?
Oh, okay, so here I didn't give you the definitions, but the definitions would essentially be of the following form. Yeah, it would be of this form. So you see the red and the blue class, I was showing you class conditional distributions. Right? So given a class, there's a Gaussian distribution, and now what would be the difference between the two is that the red class would have a mean mu that is more to the left side, and then the blue class would have a mean mu that is more to the right side. Right? So I guess I didn't write down the precise algebraic definition, but it would follow this form. Yeah. Okay. All right, so now that allows us to make a prediction, right? So if we can compute the posterior, then we have a distribution over the classes, and then we can make a prediction. And in practice, for some applications, really, we don't want to return what's our probability for every class, but we literally want to say, here's the class that we predict, even though we're not 100% certain about that class. And now if you need to pick a class and you've got a distribution, the natural thing to do is just to say that in the context of two classes, you would select the class that has a probability that is higher or at least 0.5. Right? So if you've got two classes, one class is going to have a probability greater than 0.5, the other one less than 0.5. So you might as well select the one that has a probability greater than 0.5 because you're going to be correct more often by selecting that class. So then, yeah, in terms of selecting a class, so the best class, then we want to find the class K that gives us the argmax here. And then if there's really just two classes, so we would select class 1 when the logistic sigmoid is greater than 0.5 and class 2 otherwise. So in fact, if I just go back to the board, so you see here we could imagine that this is our logistic sigmoid for computing the posterior probability. And then, so when we have a posterior probability that's greater than 0.5, we're essentially in this region here. And then it's natural that, yeah, we would like to select that class because we're more likely to be correct by selecting the class that has a probability higher than 0.5. And then in the other region, then we would select the other class because that's the other class that's more likely to be correct. Okay, now when we make predictions like this, it's interesting to also see what is the boundary between the two classes, right? So we saw that for k nearest neighbor, when k is equal to 1, right, then there's a nice Voronoi diagram that gives us the boundaries between the classes when we use Euclidean distance. Now, when we're using this approach, mixtures of Gaussian, what does the boundary look like? Right? That's an interesting question. It would be interesting to see, to visualize that. Now, the class boundary, you could say that the boundary happens to be precisely when the probability for each class is the same, therefore 0.5. Right? So that's the boundary. On one side, one class is more likely. On the other side is the other class that's more likely. So when we're at 0.5, now we could simplify this expression. So if I rewrite my sigmoid, I'll get this. I can simplify this so that it corresponds to just W transpose X bar is equal to 0. So what this means is that when we look at this expression, right, this is a linear expression in X, and therefore it means that our separator here is linear. So this is very interesting because it means that when we use mixtures of Gaussians, and here this is under the assumption that there's two Gaussians and then that they have the same covariance matrix, right, then we could separate our space with a line, and essentially data on one side belongs to one class, data on the other side belongs to the other class. Okay, and we can understand how this line would correspond to W transpose X equal to 0 by looking again at the drawing I've got here. So when the sigmoid is 0.5, we said that this is where the boundary should be. Now if we look at the x-axis, right, when we cross 0.5, this is precisely when A is equal to 0, and A happens to be the input of the sigmoid, which is W transpose X. Right? So that's how we can understand how we arrive at this expression here of W transpose X. Right? So is that it would correspond precisely to the x-axis here being equal to 0. Okay, and again, the fact that, oops, let me press this again. Yeah, the fact that we've got a linear expression here means that we have a linear separator, and that's why this is one of those simple models. So as we discussed in the course, we're starting with linear models, then we're going to talk about nonlinear models and more sophisticated models going forward. Right? So we're still considering simple models, and that's an example of a linear separator. Okay, so now what if we have more than two classes, right? If we have 3, 4, 5, multiple classes. So we can do the same computation that we did before. We're going to assume that each distribution has a class conditional we're going to assume that each class has a class conditional distribution that is Gaussian, and here with the same covariance matrix capital sigma. So when that's the case, right, we have the same expression as before. We can simplify it and arrive eventually at this expression here. So what I've done is instead of dividing the denominator by the numerator, right, to bring everything into the denominator to get a sigmoid function. So here we're going to leave the numerator alone, leave the denominator alone, and then simply try to simplify the way we write them. So we notice that the numerator is again a linear expression in x for the exponent. So that's what I wrote down here. And then the denominator is very similar, linear expression in x, but then there's also a summation with respect to all the classes j. So that's what we get for the posterior. And this expression also has a name. It's known as the Softmax function. Okay, and that's another function that you'll encounter very often as well in neural networks. And then you might wonder again, where does it come from? So it has its root again in a computation of posterior distributions for mixtures of Gaussians. And yeah, so that's the form. and here W would correspond to this expression. Now you'll notice here that I wrote W transpose X bar, right? So W contains both W naught and then the coefficients of X. So in here I've got W naught, which is the first part, and then this is the rest of all the other entries in my vector W. Okay. All right, so the softmax function is in fact a generalization of the sigmoid. So if I only have two classes, the softmax function does correspond to the sigmoid. It's just written a little bit differently because I haven't divided the denominator by the numerator, but it's really the same thing. But if we have multiple classes, then it's actually better to just leave it in this form. Okay, and now you might wonder, why is this thing called softmax, right? What's the relationship with max? So, okay, here we can look at the argmax distribution. So let's say that I'm computing a posterior, and I want to associate probability 1 for the class that has the highest function fj, and 0 otherwise. So then the argmax distribution would be this degenerate distribution that assigns probability 1 for the thing that has the highest value and probability 0 for everything else, right? And it's called argmax distribution because it comes from taking the argmax. And then I can do this not just with linear functions in x, but with any function in x, right? So that's why here I wrote this, where I have some function in x for every class, and then I simply give a probability 1 for the class that has the highest function. Now, this is a hard distribution, or a degenerate distribution, because there's one class that has probability 1, and all the other classes have probability 0. But what if I want to soften this, right? What if I still want to have a non-zero probability for everything? So this is where the softmax distribution comes into play, but we can see that it's really an approximation, in part because I can rewrite my argmax distribution as follows, where here this is the same as taking the limit of some base that I push to infinity, where now I'm going to take the base and put the function for each class as an exponent. And then the bottom, I just divide by the sum of the base raised to the function for every class. And here the idea is that the base, when we raise that to some exponent that correspond to the function, right? So whatever is the function that has the highest value, right? Its value, when we take that form of exponential, you know, would just increase dramatically in comparison to the other functions that are smaller, right? So it tends to make the differences much more important, so that in the limit, when my base goes to infinity, right, this will converge to 1 for the function that has the highest value and 0 for the other functions. But yeah, if I don't want something that is just 1 versus 0, but I want something in between, something that is softer, right, then I could consider a base that is finite, like I could simply consider e, and then exponentials are easy to compute as in most libraries and on computers. So then it gives us a soft version of this argmax distribution, and that's why it's called the softmax. So that's where this comes from. Now again, in neural networks, people use softmax often without really explaining this full story. The idea is often just that you have some function, and then you're using that as a way to determine maybe what should be the output, which class, and you just want to give, you know, a higher probability for the class that has the highest function, and then they use this trick of just having an exponential, right? But that's the story. That's where this comes from. And then it turns out that this exponential is also what arises when we consider mixtures of Gaussians and we compute the posterior distribution. So that's the origin. Okay, any questions regarding this? All right, very good. Okay, so now we can also look at the boundaries of the different classes when we have more than two classes. And in fact, here I'm showing you boundaries in the posterior distribution for three classes, where two of them, green and red, have the same covariance matrix. So if you recall, the covariance matrix will determine the shape of the Gaussian. Right? So the shape of those contour lines is determined by the covariance matrix. So here they have the same shape, that's the same covariance matrix. Here there's a different covariance matrix. But then, I mean, in general, we don't have to use always the same covariance matrix. So in this picture, I'm just illustrating what happens when we have three classes and then different covariance matrices. Now, if you compute where is the boundary, where essentially there would be two classes that are dominating with the same probability, it would give you those lines. Okay, so these are the boundaries, and we can see that the green class dominates here, the blue class in this region, and then the red class in the bottom left. Okay, and now you can also see that because those two Gaussians have the same covariance matrix, the boundary is a linear separator. But now if we have a different covariance matrix, the boundary is not linear anymore. Okay, so the boundary is not linear anymore, in part because if I go back, when I was doing some of the derivation, you see, if I have the same covariance matrix for all the classes, then I can simplify this term. But if I have different covariance matrices, I cannot simplify this term. And this is the term that if I keep it, now I have something that's quadratic in x, and as a result, I won't have a boundary that's linear in x, right? So my separator won't be linear. So that's part of the reason. So if we want to have just a linear separator, then we pretty much need to assume here that the covariance matrix is going to be the same. If not, then we get a boundary that is not linear. In fact, that would be quadratic. Okay. Any questions regarding this picture? Yes?
Are those BUKs taken as like the average of all points that are among that class?
Yes, very good point. So yeah, so here the mu k's are the means, right, of those Gaussians, and indeed, given a data set, they would correspond to the average of the points in that class. Yeah, so we're going to see in a moment, in fact, how do we get the parameters, like the mean and the covariance matrix, and then we'll see that it does correspond to taking the average. Okay, so yeah, so that's our next step now. So we've seen how we can do inference, compute the posterior for both just two classes or multiple classes. But now, where do the parameters of our model come from, right? So in this model, a mixture of Gaussians, we have a probability for each class. If I only have two classes, I'm going to denote the probability of the first class by pi and the probability of the second class by 1 minus pi. And then for each class, there's a conditional distribution that is Gaussian. Here, I'm going to use mu1 to denote the mean of the first Gaussian, and then capital sigma to denote its covariance matrix. For the second Gaussian, it's the same thing, but we have mu2 and capital sigma. So again, here I'm assuming that I've got the same covariance matrix for both classes. Okay, so now the problem becomes, how do we estimate the parameters of this model? In other words, how do we estimate pi, mu1, mu2, and sigma given a data set? All right, so now we're doing learning, so we're estimating the parameters, whereas before what we were doing was really inference. So given some parameters, how can we infer what is the class of a data point, right? So for learning, we saw in previous lectures that we can use Bayesian learning, maximum posterior learning, and also maximum likelihood learning. So all three of them are possible here too. But for the purpose of this course, I'm only going to cover maximum likelihood. That's in part because it's the simplest and also the one that is most often used, especially in the context of mixtures of Gaussians. Now, if you're interested, for the other two, maximum posterior and Bayesian learning, they are covered in some of the textbooks that are associated with this material. So feel free to look this up. So I guess the math is more complex. And in practice, people don't use them as often as a result of that. But it is possible to also do maximum posterior learning and Bayesian learning. Okay, so if we're doing maximum likelihood learning, now the problem becomes to find the parameters of our model that maximize the likelihood of the data. Right? So that means we start with our likelihood function. And here we want the likelihood function for a data set that includes a bunch of data points, x and y. Right? So I guess this would be the likelihood of x and y given the parameters pi, mu1, mu2, and sigma. So, okay, we already saw that for a given data point, right, and if it belongs to a certain class, like if it belongs to class 1, then this would be its class conditional, right? So it would be a Gaussian with mean mu1. But if it belongs to class 2, then it's a different Gaussian with mean mu2. And now the question is, how can we combine these two things into one expression if I actually don't know necessarily which class each point belongs to? So the trick is to simply include both expressions and then put an exponent that would correspond to the class. And here, just for convenience, even though I've got classes 1 and 2, I'm going to label those classes with 0 and 1 so that I can use an exponent where whenever y is equal to 1, then that term is active. And then whenever y is equal to 0, then this disappears. It just, it's as if it wasn't present. And then same thing here. If it's 0, then this term will be present. And then if y is 1, then this term disappears. Right? So this is a nice way to combine the class conditionals for the two classes into one expression. But then to make this work, instead of just calling my classes class 1 and 2, I'm going to use labels that are 0 and 1. So that's why here I'm assuming that yn is an element of the set 0, 1. Okay, so this is the probability of obtaining a point with a certain class, and then I'll have, let's say, n data points in my data set, so I'm going to take the product for all my data points. So that's my likelihood. Now I want to find which parameters would be the best in terms of maximizing this likelihood. So I've got an optimization problem, and then I can simply write it in this form. So now this optimization problem is really just the max of this. But in general, if we're doing a maximization and we've got a product, that means it's a nonlinear expression and it's going to be complicated. So we're going to use the trick that we saw before, where we're going to take the log of the expression, right? Because the log does not change the max. So if I take the log of this expression, the product becomes a sum. And then the log of something raised to an exponent yn just becomes yn times the log of what's inside. So I've got log of pi times the log of the Gaussian. And then the Gaussian is an exponential, so the log will cancel with the exponential. So I'm just left with the exponent here. Okay, so it turns out that here really taking the log can simplify a lot of things. So we're using that. And then for the second part, we have the same trick. So we're going to have 1 minus yn times the log of what is in the expression here. So, okay, so that's our optimization problem. And then when you look at this, you might say, well, sure, we got rid of the product, but that doesn't look much more pretty, right? So it's still an expression that looks scary. But it turns out that if you're a little bit familiar with optimization, this expression is actually nice. So this expression has a form that is concave and therefore has a single global optimum. So let me just draw this so everyone understands. Okay, so the objective here of maximizing the log likelihood corresponds to a curve that has a shape like this. So it has a shape that corresponds to a hill where there's a single global optimum. And so in that sense, it's a concave function. And then we can simply use the trick that at the maximum, the slope is going to be 0. So we're going to set the derivative to 0 and simply isolate the parameters. Okay, so this turns out to be an easy optimization problem. It doesn't look like this when you look at the expression, but this is where with a bit of knowledge about optimization, this would be actually an objective that you would feel good about. Okay. All right, so now if we take the derivative with respect to, let's say, our first parameter, which was pi. Pi is the probability of the first class. Then you expand this. So if you just do the math, take the derivative, you would get this expression. You can reorganize the terms. And then at the end, when you isolate pi, you get this expression. Okay, so it's a nice little expression. Now, can anyone interpret what this corresponds to? What is the meaning of this expression? Say that louder. Yeah, this is a sample mean, okay, the empirical mean. So here we have, well, pi is denoting the probability of one class, the class that here we would be labeling with 1. And then this is essentially taking the sum of all the data points, so essentially counting how many data points are of class 1 divided by n, where n here is the total amount of training data. Okay, so this is essentially computing the fraction of the data that belongs to class 1, right? And this is beautiful because if you didn't see any of these derivations, right? And in fact, if you just went on the street and asked somebody, I've got a data set and I need to estimate a parameter in my model pi, which is the probability that a point belongs to class 1, and you ask anybody on the street, given a data set, what would be your guess, right? They would probably just look at the fraction of the data that belongs to class 1 and set pi to this fraction. And it turns out that this is exactly what we obtain by maximum likelihood. So this is beautiful because, I mean, it's nice when something intuitive has a nice formal derivation, and that's what we've just shown here, that the principle of maximum likelihood confirms that this intuitive approach makes sense. Doesn't mean that it's not the best estimate, but it's an estimate we can justify. Okay, if we do the same thing with respect to the mean mu1 for class 1, then we get again the derivative, set it to 0, isolate mu1, and then we arrive at this expression. Same idea, so this expression is going to be the sample mean or the empirical mean of the data. So here the way to interpret this is that I'm going to associate with class 1 label 1. So if we've got label 1, it means that points of that class have a yn equal to 1. And then I'm taking the sum of all their inputs divided by how many points are part of class 1. Okay, so this is essentially the mean of their inputs. And again, naturally, if we didn't do any of this derivation, this is what you would arrive at. So now we've got a justification for that. And for class 2, it's the same thing. Here for class 2, it's a little bit counterintuitive, but I'm going to assume that I'm using the label 0 for yn. Right, so we've got two labels, 0 and 1. I'm going to use label 1 for class 1 and label 0 for class 2. So when I use label 0, then 1 minus 0 here gives me 1, and I'm effectively taking the average of the data points that are part of that class. Yeah?
So is the y the output function, like the component of the Softmax?
Right, so okay, so y, okay, in this particular context would be what we have as part of our data, right? So we've got data that corresponds to x and y, so y is the output, but then in this particular case here, it's not produced by our model, right? It's what we're given as part of the data. Okay, so I guess in some other slides I would have called that the target. Yeah. Yeah, so that is the target here. Yeah. Yes?
Can mu1, mu2, and the covariant matrix achieve the maximum likelihood function at the same time?
Can mu1 and mu2 achieve?
As you take the partial derivative with respect to mu1 and mu2 separately.
Yes.
But can they like maximize the likelihood function at the same time?
Yeah, so they're going to maximize the likelihood function at the same time. So here, it just so turns out that when we take the partial derivative, right, so with respect to mu1, we don't see anything about mu2 in here, right? So we end up with an equation just about mu1, so we can isolate mu1. And then when we do the same thing for mu2, then we're going to end up with an equation just in mu2, we isolate it. So effectively, we are finding what are the right values for mu1 and mu2 that will jointly maximize the likelihood. Yeah. Now, in other settings, we might end up with equations that have both mu1 and mu2 together in the same equation, and then we have to solve a system of linear equations. In fact, this is what you guys had to do for the last part of assignment 1, right? So there was a system of linear equations, and then you had to isolate each variable. But here it just turns out that each variable is already alone in its equation, so it's a lot simpler. Yeah?
So at first, what is the x? X is the probability corresponding to y.
Oh, so x is the input of our data point. So we've got a data point that has both input and output. So x is the input, y is the output.
Oh.
Yeah. Okay, and then the last parameter that we need to estimate is a covariance matrix. Here again, if you recall, we assume that there's a single covariance matrix for all the classes. Under that assumption, when you take the derivative, set that to 0, you end up with this expression, which can be interpreted as follows. So this is really a linear combination, in fact, a convex combination of the empirical covariance matrices for each class. So here S1 is really the empirical covariance matrix for class 1, and S2 is the empirical covariance matrix for class 2. And now we're taking a convex combination weighted by how many data points belong to each class. So this is pretty neat as well. Okay, so I guess this completes this set of slides. Are there any further questions regarding this material? Yes?
So why do we need to get the maximum likelihood estimation of all these parameters before we can just use the Bayesian to actually calculate the class?
Okay, yeah, good question. So I guess, yeah, here at the beginning we talked about doing Bayesian inference, right? And then in the second part we talked about doing maximum likelihood for estimating the parameters. And here, this might be a little confusing because it feels like we're employing two techniques, Bayesian learning and maximum likelihood learning, but really the first part was not learning. It was just doing inference. Once we have the parameters of our model, right, how can we use this model to compute a class or make a prediction for that class? And then this is where we use Bayes' theorem. So Bayes' theorem can be used for all kinds of things. It can be used to do Bayesian learning, but it can also be used to do just inference. So we used, in the first part, Bayes' theorem to do inference, but this was not learning per se, right? And then, so there I assumed that I had already the parameters of my model, whereas in the second part, then we answered the question now of where do the parameters come from. So that's where the machine learning part is. And then for this, we did maximum likelihood. But as I mentioned in some earlier slide, we could also do Bayesian learning. So yeah, so here you see I only covered in these slides how to do maximum likelihood learning. But it is possible to do maximum posterior learning and also Bayesian learning. But for the purpose of the course, I'm just covering maximum likelihood learning. Any other questions? Okay, so if there are no further questions, then let's stop here. And next class will cover an extension of this, again for classification.